So far, we've talked about what capacitors are and how they work. Next, we'll talk about using capacitors in circuits. Generally, we never have just one capacitor in a circuit. We have a whole bunch of them, so they need to be connected to each other. There are two fundamental ways they're connected, and the first one we'll talk about is when capacitors are connected in series. What that means is that they're all connected in a row or in a line. Say we have three capacitors, what we would do is come out of one terminal of the battery, plug into one end of the capacitor, we would come out the other end into the next capacitor, out the other end into the next capacitor, out the end of that one with a wire and back into a battery. So they're all connected in a row or maybe in a line, you might say. So that's what it means to be connected in series. Let's think about what we know about capacitors connected in series. And first, we'll think about what happens when we connect a battery to some wire and connect it up to a capacitor. Well, what happens is that we get charge plus Q flows out of the battery due to the chemical reactions into the battery. That charge plus Q flows to the wire until it hits the top plate of capacitor 1. It gathers up on that top plate because it can't jump this gap. Then what happens on the lower plate is plus Q is repelled away from it. The effect of that is to leave the bottom plate with a charge of negative Q, and that charge of plus Q travels down until it hits the top plate of C2. That leaves that one with a charge of plus Q, repels charge Q from the lower plate, that one's negative, and that charge hits plate C3. That repels a charge Q, so the bottom plate is negative, and then the charge flows back around. So this is what happens when we have a bunch of capacitors in series, and the really important part is to recognize that every single capacitor connected in series all has the same charge. So series means same charge. Well, what about the potential? The battery is a source of potential for the circuit, so whatever potential gets put out gets used up across the different capacitors. It's like conservation of energy. The potential energy put out by the battery gets used up by the capacitors. So each capacitor is going to have a charge of Q. Each capacitor is going to have a potential that we might call delta V1, delta V2, and delta V3. And the total potential put out by the battery is divided over the three capacitors. So it all has the same charge, but the potential gets divided. Okay, let's use these concepts to figure out how we would analyze capacitor circuits. To do our analysis of our circuit, we're going to introduce the idea of an equivalent circuit. What an equivalent circuit means is we take out our three capacitors, we replace it with a new capacitor, but we get equivalent behavior. This equivalent capacitor, it's going to have the same charge that these three capacitors had, and it's going to have the same potential, delta V, of the battery across it. So that's what it means. We replace the capacitors in series, in this case C1, 2, and 3, with a single capacitor. C equivalent has net charge Q, same as the other circuit, and it has potential delta V. Here we might remember the relationship between charge and capacitance. This equivalent capacitance is going to be equal to the charge divided by the potential. Okay, what we want to do now is we want to put this idea in this equation, and then we want to do our delta V1, 2, and 3 in terms of our C1, 2, and 3. And let's see where that takes us. Okay, so from this equation, C equivalent is Q over delta V. That means delta V is equal to Q divided by C equivalent. I'm going to fill that in my equation down here. Q divided by C equivalent. This is equal to delta V1. So now let's come up here to this expression. Delta V1 is going to be equal to Q divided by C1. That comes in down here. Delta V2 likewise is going to be Q divided by C2, and delta V3 is going to be Q divided by C3. That can all come in the equation. Q divided by C2 plus Q divided by C3. We'll notice we have a Q in the numerator in every single expression, so we'll divide both sides by Q. And that's going to lead us to the final result, 1 over C equivalent for a set of capacitors connected in series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And if we had a bunch of capacitors, we would just keep adding them up until we included all of them. So this is our expression to find the equivalent capacitance for capacitors in series, or maybe connected in series. In this example, we have a set of 3 capacitors. They're connected to a 30-volt battery. We're asked to find the charge on each of these 3 capacitors and the potential across each capacitor. So what we know is that each of these 3 capacitors will have the same charge because they're connected in series. So series, they're going to have the same charge, and the potential is going to be split, because that's how capacitors in series behave. To get started, why don't we draw an equivalent circuit? So in our equivalent circuit, we're going to have our 30-volt battery, and that's going to be connected to a single equivalent capacitor. This equivalent capacitor is going to have a capacitance, which we can find using the equation we derived before. So 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. Oops, I just wrote a 3 instead of C3. All right, to find our equivalent capacitance, let's go ahead and put our numbers in. I've got 1 over 12 microfarads plus 1 over 4 microfarads plus 1 over 6 microfarads. If I use the common denominator, I've got 1 over 12 plus 3 over 12 plus 2 over 12 microfarads. Gives me 5 over 12 microfarads. I'm kind of a fractions person, that's why I go for the common denominator. If you're a numbers person, you might just go ahead and do that on your calculator. So 1 over C equivalent is 5 over 12 microfarads. So C equivalent then is 12 microfarads divided by 5, which gives me an equivalent capacitance. My goodness, I did 1 plus 3 plus 2 equals 5. 1 plus 3 plus 2 is equal to 6. Let me fix that up. This is what I get for trying to do lectures in the evening. 12 over 6 is 2 microfarads. Okay, so my equivalent capacitance is equal to 2 microfarads. As a reminder, micro means times 10 to the minus 6. So there's my capacitance in SI units. Okay, what I can find now is I remember that this equivalent capacitance has exactly the same charge as each of these 3 capacitors. So why don't I say, use my equation, C is charge divided by potential, and let's find the charge using my equivalent capacitance. Okay, so I know that C equivalent is the charge on my equivalent capacitor divided by the potential across my equivalent capacitor. So my charge Q is the equivalent capacitance times the potential across it. The potential across it is 30 volts, the full potential of the battery. So that's 2 times 10 to the minus 6 farads times 30 volts gives me a net charge on that equivalent capacitance of 6 times 10 to the minus 5 coulombs. If you prefer, you can write this as 60 microcoulombs. And this is going to be the same charge on each of my 3 capacitors. So Q1 equals 6.0. Actually, I think I will write it in microcoulombs just because it'll give me a little bit more space. Q1 is 60 microcoulombs. Q2 is 60 microcoulombs. And Q3 is 60 microcoulombs. All right, now that I know the charge and the capacitance, I can find the potential across each of these. Let's find our potentials now. Since C is Q over V, then V is Q over C. So let's use that. So delta V1 equals Q divided by C1. So 6 times 10 to the minus 5 coulombs divided by 12 times 10 to the minus 6 farads gives me a potential of 5 volts across that first capacitor. Okay, second capacitor, I'm going to have to take up a little more room, is delta V2 equals the charge 2 over the capacitor divided by C2. So 6 times 10 to the minus 5 coulombs divided by 4 microfarads, or 4 times 10 to the minus 6 farads. This potential turns out to be 15 volts. And then for our last one, delta V3, got the charge divided by C3. So 6 times 10 to the minus 5 coulombs divided by 6 times 10 to the minus 6 farads gives me a potential of 10 volts. What we might notice here is what we set out to say to be true is that our net potential here, 10 plus 5, 15 plus 5, adds up to be 30. This total potential gets split over those three capacitors.